In the year 1850, physicists and mathematicians were about to discover a concept that would completely transform the views about the universe. That one theory that was about to answer most of the unanswered questions, the law that is seen in almost all branches of science.
Since Newton published his law of gravitation, the orbit of planets seemed predictable. Predicting the universe was just limited by one's computational power. But this new concept was going to make the universe even more predictable. Before knowing about the law that was about to revolutionize not only physics but the whole world of science, we should answer one question.
The question is, heating a system requires energy to make the system attain a higher energy state. But why would you need energy to make something attain a lower energy state? Then where does the energy we are providing to cool that thing is going? The answer lies in understanding how a heat engine works. A Stirling engine is a heat engine which works by the expansion of air. When it is heated on one side, the air pushes the piston and moves the crankshaft, extracting useful energy into work. Every engine works under a simple rule. That is, heat in motion can put things in motion. The heat engine could have moved in many directions, but the heat flows in one direction, from higher temperature to a lower temperature. So, to set heat in motion, we need temperature difference. The Stirling engine can even work on by cooling on one side. But wait, how can you use something as fuel if it's not providing the energy? If the engine was only cooled on one side and leaving the other end in room temperature, the heat from the surrounding fuels the engine, as the cold part doesn't provide the heat but provides the temperature difference. While we are cooling something in a refrigerator, the kinetic energy of the atoms are transferred to a fluid called refrigerant, and then the fluid is compressed and the heat which is contained is dissipated to the environment. And that work needs energy. To answer our first question, where does the energy goes? It goes to the environment it is surrounded by. It has a specific name called Gibbs free energy, and this is the energy which supports some reactions called spontaneous reactions. Basically, Gibbs energy is like a storage device which stores the energy which is dissipated while creating the temperature difference. But still, there's one question left unanswered. That is, why do we need energy to cool something? And the answer lies in the same place. The Stirling engine works even better when it is cooled on one end and heated on the other. But how much better can an engine become? The best engine that the laws of nature can permit us to build is an engine that can convert all the energy we provide into work. This idea was proposed by Carnot, and that's why it is called a Carnot engine. But building that engine is considerably nearly impossible because of that one thing, which all of the scientists were looking for it at that time. Every engine not only obeys the law of conservation of energy but also the laws of thermodynamics. More specifically, that we are looking for the second law of thermodynamics. The Carnot engine obeys these laws so perfectly that it becomes 100% efficient engine. Because the Carnot engine always maintains its ratio of heat and temperature equal, that is, in other words, it conserves entropy. Some call it the measure of how spread out the heat is, but the concept is same. That is, when heat flows, it's always in one direction. That is, it spreads out from high to low temperature till the state of equilibrium is reached. So, thermal equilibrium is the most spread out state of the heat flow. So, that is the state of highest entropy. When you heat an ice cube, it melts, and the kinetic energy of the ice has increased as well as the entropy of it. Due to this, the molecules which were arranged in order has now become more chaotic. That's why gas has more entropy than a liquid than a solid. As we know, heat always spreads out. That is why entropy always increases. Even if you try to decrease entropy locally by placing molecules in a not so random way, you are increasing the entropy by doing work and spending energy. And almost every time you spend energy, some of it is always wasted. So if the energy is spent, then of course the entropy is increased. So no matter how hard you try, you can't compress something without spending energy. To even decrease the entropy locally, we need energy. Now you know where this is heading to. That's the answer for this question. Why we need energy for cooling something? When we are cooling something, we need energy to reduce the entropy locally. The water has more entropy than an ice cube, so to reduce the entropy of the water molecules locally, we need supply energy, even though it's increasing the entropy universally. In a bigger scale, all the stars and galaxies reach a state of equilibrium, the state of maximum entropy, a point of time where the universe doesn't have enough useful energy to sustain any process. The state of universe is so homogeneous that it's called as the heat death of the universe. The universe has attained a dark state where the atoms have lost their energy, the stars have faded out, the black holes have evaporated by Hawking's radiation, the orbit of planets decayed, the giant source of energy have shut down. The universe left with no purpose to do, just getting colder and colder in the eternity of the time. Entropy was like the hidden variable in almost every topic of science. One such place where it found to be very useful was in probability and information theory. According to information theory, an event to have more useful information, it should have more entropy. Let's just say we have three types of file, each with a length of 32 bits. One which contains all of the bits as zeros, and the second one has all of the bits in ones. Third one contains a random zeros and ones. Now the question is, which is easier to compress? They are the files with same type of bits. According to information theory, both files are considered to contain zero entropy and has no information in it, as both have a specific pattern which is easier to predict. The number 0 is obtained by the formula for the entropy as log of 1 over probability of the entries, then log of 1 is 0. So does the information they contain.
But the third file seems to have no pattern, so it has 2 power 32 possible configuration. So has an information of 32 bits in terms of log to the base 2. So the information contained is the entropy of the system, and the entropy increases when the possible configurations are high and the probability of each events are spread out evenly. So that's why a dice toss has more information than a coin flip. According to information theory, the most incompressible file is the one with highest entropy. As entropy is seen everywhere in the universe from large scale to the atomic level, the structure of a molecule is decided by the configuration with highest entropy of energy distribution with respect to all the atomic bonds. And in crystal formation, the atoms in the crystal arrange themselves in such a way that it has even distribution of its internal energy. It kind of amazes me, the law which is seen in every corner of science resulted as an answer for a simple question called why, and the curious nature of human to look for its answer.